It's my pleasure to welcome you this evening to the 19th Faculty Award Lecture. I have a great evening planned for you. I'm Dr. Dan Nogales. I'm the Dean of the College of Arts and Sciences and have the pleasure of serving for the undergraduate program here. This is my 20th year on campus, in which most of this time that I've worked here with Dr. Anstine and Dr. Case, who will also be presenting tonight. Before we get too far going, Dr. Webb is supposed to be here introducing the speaker. He is sick with the flu, unfortunately. I'm not sure what that says about an immunologist not getting a flu shot. But so the schedule for this evening will be an introduction from me, will be a presentation from our presenter, a rebuttal from another colleague, and then if time allows, there'll be questions. And of course, we'll save enough time for refreshments at the end. So please continue the conversation that we have after the presentation with refreshments. I have a script here which I probably won't go through and read, but I just want to say a little bit about NNU, and we have quite a few guests here this evening. NNU is a place in which we allow our professors to express their ideas. And we argue, and we disagree, but we are one body in Christ. And so we agree on the things that are ultimately important, and that is on salvation and the love of Christ and the triune God. Other than that, we like to debate on a few things, and there's a few folks in the audience that probably will do that during some questioning. I've known Tim for quite a while. We were at Point Loma Nazarene University together, a little older than him, and I was a very big surprise when I was in graduate school at University of Nevada, Reno, that Tim became my next door neighbor as he joined University of Nevada, Reno as well. And so we were in graduate school together for, me a little longer than Tim. But in any case, I went off to a postdoc, and Tim went off to a postdoc at UC Berkeley. So Dr. Anstine is a graduate of a Nazarene University, and obviously was trained in graduate work in organic chemistry through what we both share is a sort of the academic grandchildren of a fairly famous organic professor, Carl Gerasi, who invented the birth control pill. And then off to postdoc at UC Berkeley by another very famous organic chemist, Professor Dalvin. So Tim is well trained to address the issues of both science and faith, and that's what we'll do tonight. The choice of the lecture was competitive, and it went through a faculty committee which selected Tim to give you this award lecture tonight. So without any other comments, I'll turn this over to Dr. Anstine, but first I'd like to recognize Suzanne, his wife here this evening. And so let's continue the applause for Dr. Anstine.
Thank you, Dr. Nogales. I appreciate that. I would like to thank you for coming out tonight and acknowledge the real Dr. Anstine, I always call her. She's the graduate from here in '93, so it's kind of neat that she's got that connection. So I'd like to thank a few people before I start. Just Dr. Strohmeyer and Dr. Gismondi spent quite a bit of time with me just kind of working through my own thinking process, my own thought process in this, because I'll tell you, as a trained organic chemist, I am kind of a newbie to philosophy and history, but I enjoy those areas. And so when I jump into something like this, because science is so philosophically laden, I want to have my bases covered a little bit at least, so my chemistry has a background on which actually hopefully makes sense, and maybe it won't, maybe it will. So tonight, I can't do anything in life. I know it sounds kind of weird at a faculty lecture, but I got to start with prayer. Lord God, thank you so much for this time right now. Thank you that it's about you, Jesus. Thank you that you are what it's all about. And I ask tonight, Lord, that this would bring glory to you. I ask that our conversation would bring glory to you. You know that's my goal in life. You know that's why I am here at this school, Lord. And so this is all for you. May you speak, may you change, may you challenge us tonight in your name. Amen. So whenever we start a talk like this, I always have to be careful that people hear the words that I'm saying and we're using them in the same context that I'm using them. Especially in this conversation, so to speak. Because this word right here is very, very loaded. This word is very loaded, the word philosophy is very loaded, and the word science is very loaded. So those three words, if you don't know what I mean, and I'm not communicating that the same way you're thinking about it, then we're really not going to have a fruitful night. So the very first thing I want to do is talk about what I mean by evolution and what I do not mean by evolution. There are three primitive names, or primitive, or kind of distillate definitions of the word evolution. And the very first is this primitive word called change over time. I know of no scientists that disagree with that definition, so we can move quickly past that. Unfortunately, a lot of people, when they use the word evolution, this is what they mean. Things change over time. And no one would argue about that, right? Things change over time. People change, birds change, dogs change, etc., etc. The second definition that I will not be using tonight is actually this one here, descent with modification. The question here is, do mice and chimps share some form of a common distant ancestor? All right? This is not the realm of organic chemistry. This is the realm of biology. But I do want to just say that that is another definition of this word. Okay? And if you look at the grand scheme of this definition, it's pretty robust. And again, this is more in the lines of the geneticist and the biologist than my realm. When I use the word tonight, evolution, I want to be very clear that I mean this definition right here. In the beginning, there was nothing. And out of the nothingness, there was all of a sudden something. And in the something, there were laws that came into being that brought everything into being. That is the definition that I'm using tonight. It's a metaphysical definition of our reality, and hopefully we can flesh that out and have some conversation about that maybe down the road. We typically have grand schemes that look like this. And when I say a grand scheme like this, as an organic chemist, I have to pause, and that's why I put my name in the hat for this lecture tonight, because I think there are three areas as an organic chemist that I need to pause and say, hold on. Before I buy into this mega narrative, I want to ask some questions, and that's what we'll be doing hopefully tonight. Science is the second word that I'd like to define. Science has two presuppositions, or two things are before science, if you will. The first is mathematics. Okay? Mathematics has to be there in order for there to be science. 2 plus 2 needs to equal 4. Yesterday, today, and tomorrow, somewhere in the universe, somewhere on Earth. Otherwise, we really don't have a discussion, because we need something objectively true to be able to rationally look at the world around us. The second one is philosophy. Okay, science is heavily laden with philosophy, so I want to pull some of that out tonight, again, before we jump into chemical evolution. All right? So let's take a look at science. I was in a debate a few years back on NBC with Eugenie Scott, who is the national director for the high school curriculum. And one of the things I saw during this debate was her going back and forth between two definitions, if you will, of the word science. And she would go back and forth between these like they were the same. And I was kind of like, whoa, hold on a second. And if you're not trained in hearing that, then it's really important for me to flesh that out. Because when I say science, I want to mean what I say. So you can roughly think of science, the two different sciences. And again, where the line of demarcation is fuzzy. And we could go into Papin or Kuhn or Lakatos, and we could look at all these philosophers that have tried to flesh all this out. But for tonight, what I want to get across is, and hopefully you'll see this, there are two realms of science. There is science, and there is science. It uses the same word, so it can become a semantic discussion, and I don't want that. So, when I say science, and you can see this here, I have a lot of things that science has brought to the plate. Okay, we can call these technological advances. iPods and artificial hearts. And here's penicillin, a remarkable thing. And how does penicillin react within the realm of this protein? All right? What I would call this, and loosely call this, and again, some philosophers don't like this, but this helps me and helps my students see that there are these two realms. One is operational science. How things operate. How does penicillin operate? How does penicillin come together, hold together? Okay? The other realm is concerned with how things originate. loosely. Again, I know it's going to be hard to, anyway, I'm just going to leave it there. If you look at this, how did the first cells originate? How did the eye originate? How did the brain originate? How did man originate? And though both of them use science, and both of them use current science, somehow we have to make a demarcation between those two. And one of the persons that attempted to do this was Karl Popper, a philosopher in the mid-20th century. And what he roughly said, and again, this is rough, because again, Kuhn's going to come in with his paradigms, and Lakatosh is going to say, no, it's in between, those two guys didn't have it right, and there's a lot to this. But tonight, for the most part, I want to say there's a difference between operational science and historical science. There's a difference, but yet there's a similarity. So let's flesh this out just a titch. Popper says this: insofar as scientific statements speak about reality, it must be falsifiable. And insofar as it is not falsifiable, it does not speak about reality. Now, I think that goes too far, to be honest with you. But what I do think that helps me understand is that the realm of the now science is what's happening. How does the universe go right now? Right now. How does the universe operating and carrying about right now? What's the electron doing? What's the penicillin doing? How's the penicillin connected together now? And so roughly, I would call this now science. I can go across the lab right now, and I can add these alkali metals to the halogens, and I can have exothermic reactions, and I can study it right here and right now. Notice, this is then science. It's science that was back then. And it's going to be hard to falsify something like the Big Bang or even the origin of the cell. How do I conclusively say, this is how the cell originated, this is how the brainstem originated, this is how... You see what's going on there? There's two different realms of science. Now, that said, this realm of science does use falsifiable techniques. What it does is it extrapolates back and it says, I assume that the speed of light has been what it is today at starting point 0, therefore this. Or I assume and I project or I push back or I say that because I know what it is now, I'm going to assume it's always been that way. Or it was always that way, so it is that way today. So I still use falsifiable science now, but I'm looking back then. And when we deal with the origins question, that's very important to be able to understand the two different realms. Because I, as a chemist, can go in the lab and I can do a lot of these reactions, and I can show my student, and they can falsify it. Now let me say this, falsifiable does not mean false. Just like breakable does not mean broken. A vase is breakable when it sits on the shelf. You can find out if it's breakable by knocking it off. Sure enough, it broke. Okay? That's what we mean by falsifiable. It means that I can study it and see whether or not, when I add sodium hydroxide and hydrochloric acid together, it forms an exothermic reaction. Okay? You see that? But how would I falsify a singularity? How would I duplicate that in the laboratory and say that's exactly how this happened? That's tricky, if not impossible. Okay? So you have those two realms. The second realm is philosophy. Now this is an interesting discussion. You're saying, why does this do with organic chemistry? Trust me, I will eventually land this plane, I hope. Scientifically, historically, science, when you look back over the history of science, science was considered to be an activity with a goal. Let that sink in for a second. It was an activity with a goal. The activity was using the scientific method. And most of us have had enough science to know there's a scientific method of hypothesis and study and testing and reconfirming and publishing and getting more money. And it's a cyclic process. Okay? It's a scientific method that came out of some amazing minds in the 15th and 16th century, 17th century even, as it's being refined a little bit more. The goal, historically in science, was to discover truth about the creation. So it was an activity with a goal. Activity is a scientific method to discover truth about the creation. And if you look at some of the historical comments that have been made, some of the best and the brightest minds in all time in science, one of which is Johannes Kepler here. Here we are concerned with the book of nature, so greatly celebrated in sacred writings. It is this that Paul proposes to the Gentiles, that they should contemplate God like the sun in water or in a mirror. Why then, as Christians, should we take any less delight in its contemplations? Since it is for us with true worship to honor God, to venerate Him, to wonder at Him. The more rightly we understand the nature and scope of what our God has founded, the more devoted the spirit in which that is done. What a remarkable testimony from one of the most brilliant minds in all of science. In fact, Kepler was the one that really fleshed out the three planetary motion laws that led to gravity. So it's kind of an important moment in the history of science. The next one, probably talked about as the #1 scientist of all time, arguably, is Newton himself. What did Newton have to say? This most beautiful system of the sun, planets, and comets could only proceed from the counsel and dominion of an intelligent and powerful being. This being governs all things, not as the soul of the world, but as the Lord over all. Now, the reason why I bring this up is because that I believe in history, in the history of science, you don't have to go back very far to see that men and women were conducting research in a specific way to be able to flesh out truth about the world that they saw around them. And there was a rational order to this. In fact, Einstein says it this way: I want to know God's thoughts, the rest are details. Okay, that's pretty succinct, and you can flesh that out, probably write a whole thesis on what he meant by that, but it's still a pretty germane comment by Einstein. If you look historically back and go back to the Greeks, and here you have Pythagorean and Plato, they talked about how the order, they called it the form that was out there, they talked about how the world was orderly, rational, and intelligent. Okay? This they called, by the way, the Logos. The Logos out there was this rational order. And as Newton and Kepler said, we're really thinking God's thoughts after him. We're following him in his thoughts, if you will. This Logos, the Greeks believed that if one lived in conjunction or within harmony with this form out there, this Logos, then their life was the best life possibly lived. Now, the Christian mind, or the biblical mind, differed a little bit on how far to take the Logos, and you get into necessity and a couple of the different qualifications. We can say that for a different night. But nonetheless, both the Greek and the biblical thinking was that the universe was rational. There was a rational order to the way it was put together. Okay? So when I asked, thankfully, my pastor at Crossroads help with some of my trying to put my thinking into pictures, because pictures speak 1,000 words. This is the way I view the history of science. I view the history of science as this Logos, and it was big enough, at least within the biblical mindset, to contain life and to hold life. But something happened in science in the mid-1900s. We had a paradigm shift, as Kuhn would say. What was that paradigm shift? The the definition of science really changed. Historically, it was an activity with a goal. Today, science can be thought more of as a game with a rule. Now, this is an important point, because again, if I am going to pose challenges to the chemical evolution model, what I'm really posing questions to is, was this a good paradigm shift? So, what was that? Well, the game is still using the scientific method. However, the rule changed. In fact, if you look, there was never really a rule. But there was a rule imposed on the way I look at the world around me. And that rule is metaphysical naturalism. Metaphysical naturalism is a loaded word. Again, that could take a whole night just to flesh out what that is, because you have methodological naturalism and metaphysical naturalism. I don't want to use a bunch of philosophical words or we'll just get lost. So let me add two more. One is epistemology. Epistemology is basically just our limits, our understanding, the origin of knowledge. Where does knowledge come from? And the other is ontologically loaded, and that is, what is the nature of reality? What is nature, really? What is really real? Okay, and you can see that you have two competing things there. Is the spiritual really real, or are the particles really real? You know, Paul would say in Ephesians 6, no, it's not the particles. It's what's outside the particles that's real. Scientists, especially metaphysical naturalism, comes in, no. There's nothing outside the particles. The particles are all that's real. And so these two things are foundational to our understanding. The scientific method is the only reliable path to knowledge. A lot of us in this room are going to challenge that. Even the philosophy professors in here would probably have a little bit of issue with that. Secondly, matter is the fundamental reality to the universe. So what happens here is I have to look at the world around me, and I have to be confined by this natural, again, all has to be answered by a natural process, if you will. In fact, Francis Crick says it this way: the ultimate aim of the modern movement in biology is, in fact, to explain all biology in terms of physics and chemistry. Okay? I'm going to reduce everything. Reductionism is a severe form of this. I'm going to reduce everything to simply the mechanics of the universe. Okay? So historically, what does that mean practically? Historically, think of it this way. This is the way I think about it, the way I teach it. If you look at the world around me, whether it's coming in from the lab or if it's coming in from the field, historically there were three ways in which I could view that data coming in. Three ways in which I could view the data coming in from the field or from the lab. One of them was what we would call law. If I see something repeated over and over and over and over again, I'm going to say it's a law. If I drop a pen and it falls, and I drop a pen and it falls, and I drop a pen and it falls, I drop a pen and it falls, other than the induction problem, I'm going to say the next time I drop that pen, it's going to fall. That's a law. There's a law. So it's repeatable. And you can see that in this pattern. It repeats. And by the way, it's predictable. I can predict what the next letter is going to be because I just saw it X number of times. The second category in which I could view the data coming in from either the laboratory or the field was through random events, chance processes. Similar to like the clouds in the sky or the pebbles on the bottom of a riverbed or the sand on the beach. Those were just random events. They're just there. They just happen. Okay? And so you can see a pattern like this and think, well, I can't really predict out here because I don't know what the next one's going to do. There's a chance that it's going to be something I can't even tell. So I can't predict with that. It's a random process. But historically, there was a third category in which the data coming in out of the laboratory and the field could be interpreted, and that was design. And if you look at this design, and you can read that up there, those of you that are paying attention, students, chemistry is so amazing. I love the periodic table, right? So how did I know that that was something? Well, there's a design component to that. There's something rationally in that I can see with my eyes and say that's a rational statement, right? The paradigm shift occurred with this. As we flesh this out, we're going to see a paradigm shift here in the mid-19th century. What happened is in modern science, again, this is historical science, this would be Kepler and Galileo, or Newton, and some of these brilliant minds in the past. Modern science comes along and says, oh, no, hold on. Natural selection working together with random mutations is really the power behind all innovations in the world as we know it. Let that sink in. What they were saying in the paradigm shift of the 19th century was that law working with chance mimics design. Law working with chance can mimic design. Therefore, we don't need design. And design was removed from science as one of the ways that we explain the world around us. So, that was the paradigm shift. If you look at Jacques Monod, of course, the French Nobel Prize winning biologist, man knows at last that he is alone in the universe's unfeeling immensity, out of which he emerged only by chance. Chance alone is the source of all novelty. Wow. All creation in the biosphere, pure chance, only chance, absolute but blind liberty is at the root of the prodigious edifice that is evolution. In fact, if you keep reading along this line of the history of science, Richard Dawkins says, biology is the study of complicated things that give the appearance of having been designed for a purpose. But it's only an illusion. Why? Because we know that these two working together mimic design. If you look at the way Francis Crick said, this biologist must constantly keep in mind that what they see was not designed, but rather evolved. So here we can flesh this out. We can start to see that, okay, these two were historically there. Currently, we don't have that realm. We are not allowed to have this filter on the data coming in from the lab or from the field. Why? Not because it's not there, I would argue, but because science has been predefined by metaphysical naturalism. We have put blinders on science, and I would call that, in my vocabulary, we have closed science. Okay? Now, what do we do with something that we see as simple as a turtle on a post? If I am in open science, I simply say, well, someone put it up there. But if I am in closed science, I have to explain how wind put that up there, or I think maybe more than likely what happened was it was actually a pond that was full of water, and it swam up there, and then a dam broke, and it just happened to suspend it there when all the water rushed out. That's how it got there. Okay? Now notice, with that second definition, I could falsify that. I could do studies of the soil around the post to see if it's wet. I could see if it could dry in a time frame that allows the turtle to still be alive. Right? And you could study that using falsifiable now science. But again, I cannot state the obvious that that turtle was put on the post by an intelligent source. That is not a place that I can discuss. That is not an area that I'm at liberty as a scientist, or at least as a credible scientist in the academy, to say. If you look at Richard Lewontin, again, the Harvard biologist, it is not that the methods and institutions of science somehow compel us to accept a material explanation of the phenomenal world, but on the contrary, that we are forced by our a priori, our acceptance of metaphysical naturalism up front, adherence to material causes to create an apparatus of investigation and a set of concepts that produce material explanations, no matter how counterintuitive, no matter how mystifying to the uninitiated, the non-scientist. Moreover, that materialism is absolute, for we cannot allow a divine foot in the door. Now, at the end of tonight, I'm going to not be arguing for a God of the gaps. In fact, I'm going to challenge us on that, because that's not what I am. That's not what this talk of tonight is about. But I want to say that right now, because people are just going to use the old God of the gaps idea. No, I am not. But let's keep going with this, and I just want to preface that. Great book, Cornelius Hunter's Science Blind Spot says, instead of merely following the data where it led, science has a framework already in place. The answer, to a certain extent, is already in place. Think of it this way. The answer to your question, student, is evolution. Now, what was your question? It's already in place. I have to give it a naturalistic explanation in order for it to be accepted. The answer is already in place. You see what's going on here? I've got blinders on to what's acceptable to be considered scientific. Evidence and logic are usurped oftentimes by a natural explanation. Okay? And I flesh that out for a real specific reason. Because as I challenge chemical evolution, which as an organic chemist, it's very important to me that this makes sense. And this area of science doesn't make sense to me. So that's why I wrestle with it, and I struggle with it, and I'm okay with that. But I want us to understand kind of the background behind this. Here's the way I would summarize my introduction. If you want to know how nature works, the best way to proceed is to just ask it. Right? That's methodological naturalism, by the way. It will eventually tell us everything we need to know about reality. There's metaphysical naturalism, by the way. The asking of questions in science has been reduced to a ritual known as the scientific method. But the answering of questions in science is confined by naturalism. And that is science today. So with that background, now it's time to start to look at what really is being said in this realm of science. The mega-narrative of evolution, again, the way I'm using the word tonight, nothing to something to everything, has three main meta-narratives, if you will. They start off with cosmic evolution. Cosmic evolution, of course, starts off with the Big Bang, proceeds to gravity condensing, and you're forming your protons and your neutrons, and then you're forming your deuterium, and more likely deuterium's colliding to form the helium. Three heliums come together to form the most amazing element on the periodic table, carbon. Okay, and all this is going on right here, guys. And all this is going on, and gravity is the driving force behind it, and the planets are forming, and pretty soon out pops Earth, right? This is cosmic. Again, this is not my realm. Dr. Packer, Dr. Lawrence, much better equipped, so that's not my realm. Neither is this my realm, biological evolution. Okay? I am not talking about biological evolution. I'll let Dr. Chase or Dr. Strohmeyer, true experts on our campus, flush that. That's not for me. But this is the part where we have cells becoming organisms, reproducing entities that move on, and through variations, okay, they can become, or they do become, or they appear to become more complex. What I am going to be talking about tonight is in between those two. How is it that minerals, that the periodic table, specifically this region right here, my wheelhouse, carbon, nitrogen, and oxygen, the building blocks, God's Lego kit, if you will. Did you guys know that? This is a total tangent. But carbon is the floor. My kids love Legos. In fact, I left home tonight with a sitter, and the floor was just destroyed with Legos, right? And I was looking at that going, that's God's Lego kit. The carbon is the 4-piece. My organic chemistry students know. Nitrogen is the 3-piece. Oxygen is the 2-piece. And hydrogen and halogens are the 1-piece. That's why I like organic chemistry. It's just an extension of Legos. I never grew up, and I never planned to, okay? Now, that said, how is it that I take these periodic table, these minerals, these elements, and all of a sudden get life? This is called abiogenesis. It's a big word for it. This, to me, is really the crux of the argument, or the problem with this grand mega-narrative of evolution, which is why I threw my name again into the hat for this talk, because I really want us to see this. In this process, in this leap from here to here, I only have thermodynamics, energy movement, kinetics, speed, and equilibrium to work with. I don't have living organisms at this point. I can't capitalize on some of the amazing things they can do. I am stuck with explaining everything through the physical laws of the universe, both in chemistry and biology, or excuse me, chemistry and physics. That's what I have to explain everything through. And I'll help work that out, because that's a very key point right there. And I would argue that chemistry does not select. Okay? It does not select, and I'll show you what I mean by that. Now, how did we go from Earth to again, these cells? There's a process, again, if you follow the grand mega story of chemical evolution. What I'm going to challenge you with tonight are 3 areas that I see as a challenge to this. Huge problems with this. And Dr. Chase, I'm sure, is going to have the other side of that. What do I do with reduced carbon? Okay, again, you're going to have a chemistry lesson tonight. I know you didn't think about that. We're going to talk about reduced carbon. We're going to talk about small organics becoming homochiral, which I think is Dr. Nagella sent both Dr. Chase and I an email last week on a lab that was doing this, and he said, oh, hey, the holy grail of organic chemistry. That's what he said in his email. I'm like, yeah, it still is the holy grail of organic chemistry. We're going to flesh that out, okay? We're going to look at that. Polymerization. How do I then go from small molecules to polymers? Okay, and then the rest of this I won't fill in for tonight. I'll save someone like Dr. Strohmeyer or Dr. Chase or whoever to fill that in. But I'm going to talk about these, really specifically this, and this tonight. Because I think that in those 3, the leap across this chasm, as I'm going to challenge, is what Richard Dawkins would say, climbing mountain probable. Okay, and then what do we do with that? And that's where we'll land the plane tonight. So let's talk about carbon. My favorite element. I've given my life, really my professional life, to studying this amazing little element. I really have. I love carbon. All my organic students in here know that, right? You guys know that I love organic chemistry. They get that over and over and over and over and over again. I love organic chemistry. I really do. I fell in love with it. I was challenged with it at Point Loma. I really fell in love with it in grad school. Right up here. But before we jump into the most amazing element on the periodic table, let's have a basic chemistry. Okay? Those of you that aren't chemists, cool. You're going to get some GChem right here. Over here we have what's called the noble gases. They're noble because they have a full set of electrons. What is full? And that depends on where they are. Argon likes 8, neon likes 8, helium likes 2. So argon is 8. It's noble. Everybody wants to be like argon, at least if you're close by. So chlorine says, argon, you've got 18. I've only got 17. Chlorine says, man, if I just had one more electron, I would look like argon. I really want to look like argon. Right? I don't think they have actually emotions, but maybe they do. I don't know if they're saying that, but that's the way I teach it. Sodium over here. Now, by the way, the periodic table, do you know the periodic table is constructed so it fits on a nice piece of paper? This is a horrible presentation of atoms, by the way, isn't it, all you my GChem students? Because this row right here actually sits right here. It's not like way over there and then way over here. This row sits right here, okay? So sodium sits right here. And it says, hey, if I just lose one, wow, I look like neon. So sodium comes along and says, man, if I just lose one, I look like neon. Chlorine says, man, if I just gain one, I look like neon. Hey, I bet we can make really good friends. And if you put those 2 together, it's a violently exothermic explosion reaction. They really like each other. And so sodium gladly gives up its electron to chlorine, and chlorine, being the one that wants an electron more than anybody on the periodic table, says, I'll take it. They come together, and we have simple table salt, right? Sodium chloride. But where does that leave carbon? Watch where carbon sits. Carbon sits right here. Carbon is in the most frustrating, disappointing, difficult place on the entire periodic table. Why? Poor carbon has to either gain 4, 1, 2, 3, 4, or lose 4, 1, 2, 3, 4. Neither of which are thermodynamically possible. I should say possible, everything's possible. Ola did that at USC. But none of this stuff, it's not practical for carbon to do that. So carbon has programmed into it a super cool solution to the problem. It says, you know what, if I can just share someone else's electrons, I can pretend like I have 8 too. And that's exactly what it does. So carbon comes along with this 4 and says, hey, oxygen, why don't you give me, because the oxygen sits right here with its 6, and says, okay, oxygen, you give me 6, and you other oxygen give me 6, and I'll give 4, and then we'll all pretend like we all have 8. And they do. And so carbon has 8, and oxygen has 8, and oxygen, and they have the octet, and they're all happy. Another example of this would be methane over here. Again, carbon says, okay, each of you hydrogens come in and give me 1, and then we'll all share, and I'll have 8, and we're all happy. But that's just part of the story. And the reason why I'm giving you the chemistry lesson for tonight is because oxygen and hydrogen don't play equally. Oxygen is the second most electronegative element on the periodic table, which means it steals carbon's electrons. In fact, oxygen has the electrons more of the time, forming this very polar bond. What that does to carbon, it actually causes carbon to be non-active. In fact, carbon dioxide is not considered an organic compound. You know that? Kind of a little trivia there. It is fully oxidized carbon. Methane, on the other hand, is active carbon. Why? Because carbon is more electronegative, and so it pulls the electrons towards it from hydrogen, and so it can react. Carbon can use these electrons here and go and build big, beautiful molecules like the biochemical molecules of life. Why is this important? Because depending on what we believe to be the original conditions of the primitive Earth, makes a big difference of whether we're going to build up biomolecules or whether carbon dioxide is going to sit there and rule the day and not do anything. See the point? The question is, how do we get carbon, active carbon and non-active carbon back and forth? How do we do that today? Let me take you on a little history. You guys know what this thing's called? Earth, right? Earth. Did you guys know the Earth breathes? How many people knew the Earth breathes? A couple of you do. Okay, Earth breathes. You want to see a picture of it? Here's the Earth breathing. Isn't that cool? You know what's going on there? What's going on there? Well, if we play this animation, if it actually works, if we play this animation, what's actually happening is we're building up carbon dioxide, right? Typically during the winter times, whether it's from the off-gassing from the ocean, or whether it's carbon being burned, or whether it's just animals in general, or a couple of things. But what happens is all this carbon dioxide builds up during the winter. And if you see during May, what happens? All the planets start to come around, and what happens? They convert the carbon dioxide, non-active carbon, back to reduced carbon in the form of glucose. And it's a very complex process called photosynthesis. So I have to wait for what? I have to wait for this biological system to get the carbon dioxide back to the reduced state of a sugar, or methane in this case, which we'll see in a second. So that being said, we take carbon dioxide through a very complex process, and out comes glucose through a very complex biochemical pathway. But hold on. Remember what I said during chemical evolution. Biology isn't at work yet. What do I mean by that? Here is the believed history of the Earth. Here is photosynthesis, about 3.5 billion years ago. Here is the first life form. Notice it's only about 500 million years between here. Okay, so I've got 500 million years to get, oh, excuse me, I got to get my life form up to here and then get photosynthesis. What form was carbon in? What is it believed about chemistry, or in the geochemical world, that carbon, what form was carbon in prior to photosynthesis? Because prior to photosynthesis, once I have photosynthesis, no problem. Photosynthesis goes through a process and reduces carbon dioxide down to reduced carbon. Reduced carbon is the one that builds up these biomolecules. Wonderful. But prior to that, what kind of form do we have for carbon? Philip Abelson is probably the leading expert in this entire discussion. Okay? His book, Aspects of Paleobiochemistry, he says this: the hypothesis of an early methane reduced from ammonia atmosphere is found to be without solid foundation, indeed is contradicted. What is the evidence for a primitive methane ammonia atmosphere? Again, a reduced state of carbon on Earth? The answer is that there is no evidence for it, but much against it. In fact, the consensus, or the leading belief about this primitive Earth, after we have this triple helium, bringing together 3 heliums in this collision to form carbon, is among geochemists, there's near consensus that the early atmosphere looked like the volcanic outgassing, which was water vapor, carbon dioxide, nitrogen, again, which is a non-active. I mean, we breathe it right now. It's not acting in our body. It's this non-active form. But the original conditions of the Earth prior to photosynthesis were all in a non-active form. That's a problem, by the way. Because if I'm going to start to be, as an organic chemist, I need carbon that I can manipulate, that I can work with. I need its electrons to move. And if the oxygen is pulling those electrons away from carbon, I have a really hard time getting that carbon to behave. And I have to go through great pains to get it to do so, and I'll show you those great pains because it's the leading theory as to how we had reduced carbon on the early atmosphere. One idea was that we used the biomasses that were down underneath the Earth to build on. Because down underneath the Earth, right, you have all these hydrocarbons down there. Those are all reduced carbons. The reason why we can burn them is because they're in their reduced state. And we can convert them to carbon dioxide and water. And we do that in our automobiles. We use their energy. But once they go to carbon dioxide, they're chemically inert, or they're non-active, and we have to wait for photosynthesis to bring those back around. Okay? So biomasses aren't a viable source because recent research has suggested that, well, maybe this biomass was there all along, and the research actually shows that these come from either thermogenesis or bacteriogenesis, which means that those reduced carbons were there from already living sources. We still have to get prior to photosynthesis in order to start building living systems. The current theory is the Fischer-Tropsch reaction. Now, I'm not going to go into deep chemistry. This would be a phone from my GChem class to actually dig out. But this is the reaction, guys. So basically, you take hydrogen and carbon monoxide and carbon dioxide under high temperatures and pressures, and you get it to convert to certain alkanes. And you can repeat the process. The biggest problem with this is that it's at high temperatures. Most organic compounds cannot survive much over 250, 280, 300 is really the upper limit for organic compounds. They just fall apart. This reaction really kicks in about 400, 500 degrees. And in fact, when you do run this in biologically friendly temperatures, you get very, very, very minuscule amounts, 0.5%. Nearly not enough to be able to build up this primordial pond that we need a heavy concentration of reduced carbon. This is a problem. And one possible solution to the problem is they arrived aboard meteorites. And this is a growing one with comets because we can look out there and we do see certain organic compounds on these bodies floating around Earth and through our solar system. But let's say they did arrive through Earth. Or let's say that they just happened to Fischer-Tropsch. There's things we just don't know about the Fischer-Tropsch or some other one that had happened to be there. That really takes us next to the biggest holy grail of the problem. So let's say we had some source, and we're going to figure out how we got from carbon dioxide to reduced carbon. Let's move on. That leads to homochirality. Homochirality. The word chiral in the Greek literally means handed. Do you guys realize your left and your right hand are not the same? Okay? This is organic chemistry. So we had GChem, now we're having OChem. So in one night, we're going to get the cool parts of GChem and OChem. You have a left hand and you have a right hand. Left hand and a right hand. Did you know there's no way you can get your left hand to be your right hand or your right hand to be your left hand? They're what's called non-superimposable. I cannot make my left hand my right hand unless I look in a mirror. Okay? There's certain molecules out there this way. Dr. Gagalis and I use this one in our sophomore organic lectures. Okay, here's R-carbone. It smells like spearmint. Okay? And here's S-carbone. It smells like dill or caraway. Right? You guys remember this from organic, right? And our nose knows the difference, and I'll explain that in a second here. Here's one all of us are probably a little bit more important to all of us. Anybody ever taken ibuprofen before? Sure, we've taken ibuprofen. Did you know that when you take ibuprofen, it's one of the few drugs that's actually given in an equal mixture of both-handedness? It's called racemic mixture. You actually take, if you take 600 milligrams of ibuprofen, you're taking 600 milligrams of the R, the right-handed, and 600 milligrams of the left, the left-handed. Your body only uses the left-handed. It just passes the right-handed on. The FDA is largely not letting us do that anymore because there's some history to the badness. Anybody ever heard of thalidomide? Some of you here probably heard of thalidomide. Thalidomide is a terrible, terrible, terrible historical fact in organic chemistry. This form here and this form here are different, the left-handed and the right-handed. The right-handed removes nausea in pregnant women. First trimester, in the late 50s and early 60s, this was given in the first trimester as an anti-nausea. What wasn't known was that the S form is a teratogen. And having a teratogen in the mother's body during the development of the fetus caused deformations of the limbs. And there's an entire generation that has the limbs that are grossly distorted, feet and hands. That's a dark side of organic chemistry, but it shows you something very important. The left hand and the right hand forms of molecules are not the same. Now, why is that important for our conversation tonight, or our talk tonight, the conversation tonight? I got to bring that word, yeah. Conversation tonight, right? Well, here it is. The building blocks of all life are the amino acids. They exist in a left hand or a right hand. You see those right here. These are amino acids, carboxylic acid, and they have these big R groups, and there's 20 of them. And this is what changes on the amino acids, and here they are. These are really the alphabet of life, or the cell. Okay? And you can look at them here. I'm not going to get into this. Take biochemistry class. It's super cool stuff. But here you have them all. And what's amazing about the building blocks of life, stay with me in the chemical evolution discussion, is that when you begin to string these all together in their secondary, tertiary, and quaternary structure, and you begin to form these into very, very complex, what we call proteins or enzymes, that are always the workhorse of the cell, that do all the work inside the cell, when they are built, they are exclusively, of the glycine, because it's achiral, they are exclusively left-handed. We are not talking 98.2, 95.5, 90.10, we are talking 100. Now remember, prior to life, we are in this pool, this pond, we only have the laws of chemistry to work with. Chemistry does not select, chemistry does equal. In fact, when you look at some of the early conditions that were run, and by the way, the Miller-Urey experiment was actually the wrong conditions. It used methane and ammonia, and the only reason why they did that, they just picked it because they say, hey, these are reducing, so we'll just go ahead and build those up. But it was the wrong, more like it was carbon dioxide. Nonetheless, what we did learn from the Miller-Urey experiment was this. Under a highly designed apparatus, where we had water, we had a spark, and we had a cooling condenser down here, all these organic molecules that fell out, and we did get, I think, 18 or 19 of the amino acids, were racemic. Equal mixtures of 50-50, left and right-handed. That's because chemistry doesn't select. The question is, in chemical evolution, where did the exclusivity of the left-handed for proteins, and by the way, DNA ribose is right-handed, exclusively, 100%. How and why, using the laws of chemistry, did that come about? Okay? Again, these are questions that I think, as an organic chemist, I struggle with that. I look at that and go, that's a good question. Yeah, I don't know what to do with that. Okay? They're synthesizing 50-50 ratio. Graham Carr Smith, a very, very important book, Genetic Takeover, says this. Homochirality is really the crux of the question of life. Probably one of the leading organic chemists was a Stanford professor by the name of William Bonner. There's an enormous gap between the origin of homochirality and the origin of life. In fact, he said, I happen to think that you have to understand the origin of homochirality before you can bridge that gap. Stepwise, one has to deal with the origin of homochirality first, and then how do you get to living organisms? See the problem? We really need these left-handed amino acids to build up life. Leading theory, right up my wheelhouse, chiral amplification. Chiral amplification is an interesting phenomenon. It does happen, it's actually pretty cool. What happens with chiral amplification is an organic chemist seeds in a little bit of pure enantiomer. A little bit of pure enantiomer is put into a flask that is really an autocatalytic reaction. What does that mean? Look at this reaction here. This is an autocatalytic reaction. I'm going to take a little bit of seed enantiomer up here. By the way, it's a 99% enantiomeric excess. That's what EE means. Okay? And I'm going to take something that's achiral, right here. And as this reaction progresses, I do see chirality. But notice, even with seeding, I see 93% enantiomeric excess. I do not see 100%. I put this in, and I let the reaction go, and I see 93. 0.2 equivalence is what that means in your stoichiometry, UG chemers. 0.1 equivalence here, and I put that in, and notice I see 55% enantiomeric excess. Even with sneaking design in. Because the question is, where did the pure seeds come from? Because if I only have the laws of chemistry to use, I still get the 50-50 mixture. Now, the reason why I say this is personal, I have actually 3 publications that deal directly with this concept and this property. This is just one of them. This is tetrahedron asymmetry. This was actually the heart of my thesis during grad school. What we did is we synthesized these molecules that form these capsules, and we made them chiral. We put these big methyl groups up here, okay? And what we showed was that if we put R methyl groups, this thing binds this way. And if we put S methyl groups, which is the other hand, they bind this way. So if all the amino acids in the body are left-handed, S-ibuprofen works. R-ibuprofen works. But if for all this, S-ibuprofen works, R-ibuprofen's worthless. And what we did with this work was to show that, wow, we can actually induce the bigger construct of these systems by pure chirality. But let me tell you from personal experience, working in conjunction with an incredibly brilliant and hardworking postdoc, it was a painstaking process to get these pure. It did not happen by chance and in the laws of chemistry, but with a lot of hard work and diligence at the bench. And in fact, crystallizing it out from brucine, which is just a brutal, it's a toxin that'll kill you like at 1 part per million, all over the lab. Awesome. Now, Bonner says it this way. Bonner says, I spent 25 years looking for terrestrial mechanisms for homochirality and trying to experimentally investigate them and didn't find any supporting evidence. That's not my words. That's Stanford organic chemist. In fact, what did he propose as a way out of this? And actually, it's a valid point. He proposed extraterrestrial seeding. Because we do see out there, we do see some chiral substances on comets buzzing around our solar system. Okay? So it's somehow, maybe it's seeded in this pond. Let's give it to them that this arrived. Or, you know, you have to think about this rationally though, right? I mean, have you guys ever seen Apollo 13? When that thing comes ripping through the atmosphere, it's over 1,500 degrees on the surface of that thing. Do you remember when I said organic molecules are, 300 is pretty hot for an organic molecule. 1,500 degrees, you start to convert things into soot and carbon and charcoal. Okay, just think of your grill on your fire, you're at home. So the last step that we're going to see tonight before I land the plane, and I'm doing pretty well, I think I have 15 minutes to land this thing, is polymerization. Stay with me. Presented 2 problems as an organic chemist that I see with this the meta-narrative of chemical evolution. The final one for me that as I look at this is called polymerization. Polymerization is not a trivial process, and here's why. What is a polymer? In order to make these biochemical molecules of life, the big protein molecules, and we can talk about their folding and stuff, which is really fascinating, because when I worked in Elan Pharmaceutical, we would make these advanced pain drugs that had 21 amino acids with 3 bridges, and to try to get these things to coil right, it was actually really hard. And so we could talk about that, which would be a different night, but really complex structures here from what? From these little beads on the string, these little amino acids here all put together. How are they put together? Well, you take a monomer and you add it to another one and they make these bonds be formed. Why is this important for tonight? Follow. Here I have amino acid 1 and here I have amino acid 2. When I add amino acid 1 and amino acid 2 together, I remove water. See that in the red donut there, the red banana? I have H2O. Water is removed in this process. So it's called a dehydration reaction. When I bring 2 monomers together, 2 amino acids together, it dehydrates. It forms water as a byproduct. Again, using the laws of chemistry and what we know about chemistry in the physical world outside of the biological system, by the way, because the biological system can overcome this. We have what's called Le Chatelier's principle. Again, basic chemistry, but what happens to an equilibrium system if I perturb it? Let's say I add a little bit of water to this side. Equilibrium just moves that way and it balances them back out. Let's say I take a little bit of the water out of this side. Well, it just moves this way and it balances back out. The point is, whichever way, if there's product in the reaction, then the reaction goes the other way. As product builds up over here, it forces equilibrium this way. Now the cells can overcome this because they're more anhydrous and they can do things because they can remove water. But we're talking about what? We're talking about prior to living in systems, we've got to address this situation. So what happens and why is this so important and why is this your third point for tonight? Water is built up. If I do this in water, what happens to equilibrium? It goes that way. Equilibrium, because the Le Chatelier's principle says, now hold on a second. When we do this dehydration reaction, we generate water. If you're going to do that in water, I'm favoring monomers, not polymers. And for life, I need very complex polymers. And if you look at the stories or what's been proposed for the primordial pond, It looks like this. Well, clay surfaces, by the way, were thrown out. There's no evidence for that. Deep sea thermal vents. Okay, deep sea thermal vents. Again, lots of water. It's very hard to do the dehydration reactions in water. We have elaborate glassware in the lab, 2 labs over. And we can actually, during these reactions, we can pull water off and we can make equilibrium go the way we want it to go. But again, that's me putting design into the system. Tidal pools, again, lots of water. Okay? Volcanic ridges is the leading current theory. It's got some merit, because if you think about this, you could concentrate up the solution. But again, you have to have this perfect balance between I need enough water to make it concentrated, not too much to drive equilibrium back, not too much heat because it will destroy the organic molecules. It has to be the perfect condition, the perfect storm right there, leading theory. But one of the other theories is also extraterrestrial origin, because there are some visions or we're finding these things on these comets and meteorites. So, all that to say, most recent book out on this entire, is a fantastic book, by the way, written by this Uwe Heinrich. The origin of life is one of the unsolved fundamental mysteries in modern natural science. The endeavor to discover some of its secrets continues to challenge researchers. It is the incapability to link chemical and biological evolution that continues to puzzle scientists. How can a mix of non-living chemicals be transformed into something as complex as the living cell? This is a problem. This is a problem. Now, what does this really do? How do you land a plane like this tonight on a faith-based community where we want to be scientists and we're also believers in the person of Christ? I'm going to propose 2 things for you. The very first thing that I'm going to propose, this is for me. This is not, you don't have to take any of this. This is for me. This is where I'm at. The very first thing is when I look at complexity like this, I'm going to bring in some level of epistemological accountability. I want to be sure that when I'm looking at the world around me as a scientist, I want to be real in what I'm letting in and what I'm not. I personally don't believe that metaphysical naturalism is a good constraint on science. I even some days question methodological naturalism. I have a little bit of issues with that as well. But metaphysical naturalism is one of those areas where I'm just looking at it going, wait a minute, there's no way you can prove by science that nature is all that matter is all that there is. What experiment did you even run to prove that? You sneak that in a priori, up front. You assume that to be true, and then you confine that on the rest of science. I don't like that. I don't like that. I like more of the open view of science that Newton and Kepler, when they discovered following God in his logic and the order of the universe. Because when I look at one of these little cheesy toys that my kids fly all over the house and they bash into it and it breaks, and they put duct tape on it to fix it, and put batteries in it, and find it when it's up in the tree. And I look at that and I say, good grief, it's amazing what engineering does today. I look at Dr. Duke's stuff that he's got in his office. My kids, they just look at his stuff and it's just, I want to be in his office and play with all his robots and toys. The amount of design that goes into that is incredible. And how can I, as a scientist, say, well, yeah, that's obvious, but this is actually obvious. This is just a product of natural processes over time. Chance and law working together develop such a beautiful system. At what level does that become absurd? I'm just throwing this out because this is where I'm at. You can take it or leave it. This is the free part of tonight. Because this is what I see happening. Historically, science had the answer. The Greeks believed it and they called it the logos. Life made sense in context of the order of the logos. But metaphysical naturalism in the 19th century, mid-19th century said, no, there's a better way to understand the world, and we had what we call a paradigm shift. And now everything in science, everything in life has to be fit into this cozy little box. And I'm seeing as an organic chemist places where this isn't so cozy. Places where I'm like, yeah, no, I don't know if I like that. Homochirality is a huge topic for me. This is what I think. I'm probably going back, old school scientist. I'm okay with that inference. But I can hear the person out there going, no, you just did it. You just did God of the gaps. No, I didn't. Popper says this. Popper believed that science advances not by proving theories true, but by proving them false and then revising them. That's a great way of thinking of science. How do you disprove? How do you chip at something and say, you know what? There might be a better way to think about this. There might be a better way to approach this. What if we could bring that to the table? Because I'm going to challenge you with this tonight. This is one of my bigger challenges. I think an appeal to the absurd goes both ways. On the one hand, it's absurd to say, I can't figure it out using methodological processes, therefore God must have done it. Do you guys know that Uranus wobbles? Well, it used to. And you know what was behind that wobble? Was Neptune. And if we'd have just said, well, that wobble comes from, God back there flicking it every once in a while, we probably would have never found Neptune. Right? So there's a place for that. But there's also a balance to this. Because the appeal to the absurd, God of the gaps, or God of the gaps. And I say God of the gaps is actually switch sides. And so this balance of this absurd, I'm not taking it to the God of the gaps, but I'm not taking it to the material process of the gaps either. And maybe the climb up Mount Probable is so hard because I've predefined what it means to climb Mount Improbable. Maybe it's not really a blind watchmaker. Maybe he's blind because I've imposed blindness on him. Do you see the rub there? Because when I see something like the alchemists, who from the 3rd century, or excuse me, from the 8th century to the 13th century, were very, very, very dedicated to get this metal right here to become this metal. This metal, look, it's only 1 proton away. How do I get this metal to become this metal? They were very, very sincere in their practice. And they spent 500 years trying to get these to convert. We look back at chemistry and go, look at them. Huh? Isn't that Mount Improbable? That was Mount Improbable. What about Mount Improbable today? And in what efforts and what pain will we go to? How will we surrender logic and intellect at the door and say, nope, it's got to be in this way? Ever lost your keys? And you looked and looked and looked and looked where you knew they were. This just happened to me not that long ago. Looking through the kitchen, every drawer. I had them in the kitchen. Where have the kids took them? Where are they? Looked and looked and looked and looked and looked. And I finally gave up. I found a second pair of keys. And that night, I found them in the bedroom. No matter how sincere I would have been for the search of the keys in the kitchen, I wasn't about to find them. However, if they were in the kitchen, my diligence hopefully would have found them for me. So what I'm saying is, I'm not going to flush it all out the door, but let's be realistic. Let's have balance. Let's have epistemological accountability. There's a balance to science, right? Would we agree with that? Now, my second one for you tonight is this. Last one. Some form of origins of Reformation. This is very personal to me. Because when I look at this creation event, what do you see? When I look at it, I see something. When you look at it, what do you see? I see something so miraculous, so amazing, so big, that I'm in awe over it. Do you think at any point in the history of the world, the universe, whatever you want to call it, there has been a non-natural event? Ooh. As Christians, I think we'd have to call water to wine, maybe? Maybe the resurrection? Maybe walking on water? Or maybe it's just a law we don't understand yet, right? I personally believe, as a believer in the person of Christ, that there are miracles. And I'm okay with that as a scientist. And for me personally, students, I'll let you know what I think. Most of the time you don't know what your professors think. Well, actually, you guys know what I think. My life is an open book. You guys know me. I think, in my life, and I'm comfortable with this, that I'm not going to fully understand a miracle, especially the creation, until the point where Jesus said, where God says, and he rested. I think I'm going to be frustrated prior to that point, saying, how did he do that? And was gravity there? And was the speed of light the same? And what was going on? Because I believe that at some point in that miracle, he's still at work. I'm okay with that. I know people in this room aren't okay with that. I don't want to get feedback that that's awful. Fantastic. That's the conversation we should be having. Because at what point, as a Christian, do you say God did have a place in creation? Just at the very beginning, where he got the ball rolling and developed the laws, and then just let it go? Well, I think we call that a deist, if I'm not mistaken. So at what level do we put the creation of the universe into the category of miracle? I don't know that. I am still working on that. I'm not saying do it. I'm saying that's where I'm at. Because I'll tell you this. My hero in philosophy and science is this gentleman right here. Some of you know him, Anthony Flew, probably the leading atheist of the 20th century, credited by several for really paving the way, his writings paving the way for the new atheist movement. His books were phenomenal. Over 40 very, 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 very well-written books on incredible topics like body, mind, and death, thinking about thinking, that's a cool one, huh? Thinking straight, evolutionary ethics, Darwinian evolution, does God exist, atheistic humanism. This was the leading atheist of the 20th century. And you know the last book he wrote before he died? You know it? Right there. There is a God. What changed Anthony Fleur's mind? Listen to his own words. The only reason which I have for beginning to think of believing in a first cause God is the impossibility of providing a naturalistic account of the origin of the first reproducing organisms. And I think those of us in this room, if we would learn something from the humility of the who's who of atheism, to say, wow, here's a gentleman whose personal life didn't match the data, but he was humble enough to say, you know what, I don't care that my professional life is going to take a huge hit from this. I was wrong. And when I let science speak, it changed my heart. That's powerful to me. There's an incredible amount of humility that's associated with that in my own journey. Hopefully what I've done tonight is throwing out some challenges. Again, Dr. Chase is going to come in and show you what I was told that the last thing you want to be is the first person to give the talk, because the second person discredits everything that you talked about the first time. So I'm going, oh, that's probably going to happen. But all that said, I want to be very clear with something. In my life, and the way I do science, and the way I teach my students, and the way I teach my Sunday school class, and the way I hopefully interact with my wife and my kids, this thing called life is real. This thing called Logos is real. In John 1:1, John starts that book with, in the beginning was the Logos. And the Logos was with God, and the Logos was God. The word John chooses to use there, for in the beginning was the Word, and the Word was with God, is Logos. The Greeks didn't take it far enough. It was conditional. The Christians said, no, it's necessary, which means it's a first principle. Creation falls out of that first principle. Logos, in Jesus, life makes sense. In Jesus, my personal life makes sense. In Jesus, science makes sense, and it makes me excited. And I'll tell you one thing that I am serious about. I am serious about that guy up there. I love him. I've given my life for him. He means the world to me, and I will continue to this day to try to glorify him in the way I do my science, the way I teach my students, and hopefully the way I live my personal life. Because that's all I've got for you tonight. But again, I look forward to Dr. Chase's input.